Hello, I'm Bahami. In this video, I want to talk about what I learned about fMRI through some of the courses I've passed. Well, we know that neuroimaging uses various techniques to directly or indirectly image the central nervous system. The approach can either focus on structural imaging, creating an image of the anatomy and the pathology or injury, or focus on functional imaging, where one tries to create an image of the metabolic or pharmacologic response of the brain or cognitive functioning. And there are many techniques that can be employed to obtain either structural or functional images of the nervous system. For instance, EEG, which is a very commonly used method for functional registration of brain function, CT, or computed axial tomography, single photon emission computed tomography, or SPECT, positron emission tomography, or PET, diffusion tensor imaging, magnetic resonance imaging, and functional magnetic resonance imaging, or fMRI, which is our main topic to talk about in this video. In this particular case, the magnetic resonance from oxygenated versus deoxygenated blood is used to create an image of the functional activity of the brain. Blood and oxygenated blood, particularly, is necessary to support brain function. So, by measuring the amount of oxygenated versus deoxygenated blood, we can get an idea of areas of activation in the brain. It has a very good spatial resolution and it has a reasonable temporal resolution, providing us with good information about the brain. But first, let's talk about the physics of MRI. We know that thermal energy causes protons to spin in our body and really in any volume. And in a magnetic field, protons assume a state parallel or antiparallel to the direction of the magnetic field. Also, the protons spin around their own axis, as well as around the axis of the magnetic field that they are experiencing. And these are referred to as low energy when it's parallel, or high energy when it's antiparallel, aligned to the magnetic field. And after a few seconds, each proton reaches equilibrium and the spin around the axis, its own axis, and the magnetic field at a steady state. And all the protons in a particular value, for example, the human brain, are aligned in the same direction along that same static magnetic field. But what is the mean of physicists when talking about T1, T2, and T2 star? T1, or longitudinal relaxation time, is the time constant that determines the rate at which excited protons return to equilibrium. It is a measure of the time taken for spinning protons to realign with the external magnetic field. And T2, transverse relaxation time, is the time constant that determines the rate at which excited protons reach equilibrium or go out of phase with each other. It is a measure of the time taken for spinning protons to lose phase coherence among the nuclei spinning perpendicular to the main field. A noteworthy point is that different types of tissue have different T1 or T2 relaxation time. In addition, in T1 weighted images and T2 weighted images, the contrast and brightness are predominantly determined by the T1 and T2 properties of tissue respectively. For example, CSF is dark on T1 weighted imaging and bright on T2 weighted imaging. Now, what's the difference between T2 and T2 star? T2 was defined as a time constant for the decay of transverse magnetization arising from natural interactions at the atomic or molecular levels. However, the transverse magnetization decays much faster than would be predicted by natural atomic and molecular mechanisms. This rate is denoted T2 star. T2 star can be considered an observed or effective T2, whereas the first T2 can be considered the natural or true T2 of the tissue being imaged. T2 star is always less than or equal to T2. Actually, T2 star results principally from inhomogeneity in the main magnetic field. This inhomogeneity can be the result of intrinsic defects in the magnetic itself or from susceptibility-induced field distortions produced by the tissue or other materials placed within the field. Well, now let's back to our main topic. In an fMRI experiment, a series of individual MRI scans is used to evaluate changes in brain oxygenation over time. In this picture, we see a series of brain images that have been acquired. So, if we extract one voxel value in each of the subsequent images, basically, we get a time series of intensity values for that spatial location across time. And then we can correlate it with whatever experimental manipulation we did. Moreover, we have a bold signal, actually a blood oxygenation level dependent signal that emerged with a delay after the neural activity in response to a stimulation. Actually, the bold fMRI is not a measure of neural activity directly. It's derived from neural activation and results from the consumption and replenishment of oxygenated blood to the brain area. So it's not a direct measure, but it's considered to be a consequence of brain activation. And now, what is the goal of the fMRI experiment? Typically, its goal is to use a stimuli to induce a certain psychological state that you are interested in. Then, use the MR signal to measure brain activity associated with that psychological state to be able to draw conclusions about where and how in the brain this psychological process is supported. And there are some types of experiment design: subtractive, parametric, conjunctions, and factorial. Subtraction design, as you can see in this picture, involves the statistical comparison of activations from an experimental condition with activations from a control condition. In other words, by subtracting the brain activity when our subject performs the task from the activity in the absence of the stimuli, you can determine the area of the brain that is responsible for that task. The other one, parametric design, which is based on exploring systematic changes in the brain responses according to various doses of the task. For instance, when our parametric variation is emotion, we follow the fMRI signal in a series of the intensity of anger, for example. Cognitive conjunction. I want to explain this type of experiment design by an example. You can imagine we have a subject and we illustrate a picture and ask the subject to only looking at the objects in the picture. In the next condition, You ask the subject to pay attention to the colors and then ask to name the objects and see in the picture. That's see in the picture. These conditions are our blocks of our experiments, that in each of them, cognitive processing is occur in the brain of our subjects. In the first block, we had visual processing and object recognition. In the second one, we have only the visual processing. And in the third condition, we have all the three ones. At the end, by identifying a common region of the brain that was active in each of the two of these tasks, for example, the first and the second one, we can say that this common region of the brain is in charge of the shared cognitive process, which in the example was visual processing. The last one, factorial design, which is the most comprehensive one. This picture shows an example of a simple factorial design. In this experiment, some goals would be to localize the areas activated more in the viewing process than naming process, which would be found through this formula. Or localizing the area that becomes more active by color fields than objects, which we can use this formula. The other category of experiment design is of timing design. The first one, block design, which could include loose comparison or tight comparison. The second one, event-related design, that could be regular or randomized. I mean, we have a periodic single trial or jitter single trial. And the last one, mixed designs, which is a combination of blocks and event-related designs. Block designs segregate different cognitive processes into distinct time periods. As you can see in this picture, in one of these simplest models, we begin with task A, after that a time for rest, then another time task A, rest, task A, rest, and a repeated series of this process. In other words, we have some blocks of experiments and control stimuli that each one lasts a few tens of seconds or a few milliseconds. Also, we have loose comparison and tight comparison in this type of design. Whenever in the rest state, we show a black screen or set a time with no voice. Actually, it depends on the type of your main stimuli. We call it loose comparison. We say it has a through rest, as the subject does not be stimulated by any specific stimuli. However, in the other type that we call tight design, we do not have true rest. I mean, even in the rest state, there is a stimulus that enhances the subject's concentration or accuracy. Therefore, the difference between loose and tight design is in their control condition. But what is event-related design? In event-related design, the stimuli emerged for less than 1 second, and the times of representing the stimulus could be randomized or regular. Very often, the subjects will have button in their hands with which they can make choices or responses depending on what type of cognitive paradigm is employed. For instance, in such an experiment, you ask the subject that whenever see the object, not the faces, press the button. Then the objects are showcased in a randomized manner. We have to know that the bold signal is lower in height in event-related design than in block design, since the events last less than in block design. And as a result, as you can see in this picture, if the same experiments be designed one time with block design and the other time with event-related design, the results could be more easily distinguished in block design results. And this is the main reason that for localization goals, block designs are more preferable. The other one, mixed design. Mixed designs are a combination of block design and event-related design. I mean, we have blocks of experiments and condition states like in block design, but during experiment state, we execute the stimuli like in event-related design. I mean, short-term stimuli in a regular or randomized manner. For instance, as you can see in this picture, there is a task that is designed to ask subjects whenever you see the triangles, do not do anything, rest state. And whenever you see circles or squares, pay attention. And as soon as you see a circle, click the button. The last topic that I want to share with you is brain connectivity. How brain regions interact with one another, which is divided into three categories. The first one, anatomical or structural connectivity, which refers to being connected one area of the brain to another area or areas through synaptic contacts, coil of nerve fibers, and the axons between neurons. We acquire this information through the MRI diffusion method, or MRI diffusion weighted images. The second one, affective connectivity, which is about the influence that the elements of a neural system exert over another. And the last one, factorial connectivity, which divided to functional specialization and functional integration. In functional specialization, there is no information about how different brain regions communicate and interact with each other. Instead, they, through the subtraction design method, find information about which region of the brain is responsible for a task or a function. While in functional integration, we specify a network for each task. And we say each task be done through the communication and interaction of different parts of the brain. Well, it was a brief outline of certain ideas, guidelines, and techniques that I had planned to cover. I sincerely appreciate your time. I hoping it will be helpful. Enjoy your day.